Any one of you, can you confirm, do you see my screen? Anyone?
Yes, sir.
Yes, sir, we can see.
Perfect. So, anyone watch this movie, this talk? Not yet?
Yes, sir.
Yes, sir.
Did you like it?
Yes, sir.
Yeah, so it was very like a new way of
Exactly. So
expressing
it
things. So
change
it was
idea how you see thermodynamics. So thermodynamics is everywhere. You just need to experience it. Great. So I'm happy that you have watched it, and others, please do watch. And okay, so today we'll be talking about little bit about phase equilibria, and I specifically kind of selected this part because it has relevance to our kind of work that we'll be doing, kind of topics that we'll be covering in molecular modeling and simulations. So again, I will kind of cover few main points or few main topics of this quite huge part of physical chemistry. And of course, I mean, you are free to go back and read the textbooks for more details, and if you want to know more about this. But I'll just mention few things and few concepts, and I'll try to convey something hopefully new. I mean, okay, the contexts are not new, but the way you understand, the way you see phase transitions, phase equilibria, and I tried to kind of keep something, something new. Let's see if it is new to you. So we'll be covering the phase transitions, Clausius-Clapeyron equation. Every one of you know this thing. Phase diagrams, and then at the end I'll show you one slide in which we can kind of utilize or take the ideas from the textbook and then do real simulations or try to understand real systems. So I'll give you a kind of a demonstration on MD simulations of phase transitions. So this is for today. Now, anyone know this picture? Are you familiar with this picture? Have you seen anywhere? Can anyone tell me if you have seen this picture or you know this place? Okay, so it's in England. So coastal. It's in the south eastern coast of England. So where there is a channel. You go from Paris, you go from France to England, and there are cliffs. These are called white cliffs of Dover. Okay, and you can Google it and check. There are very beautiful pictures of this place. Very, very fantastic. So I chose this picture for a particular reason, and probably you have already guessed it. I wanted to describe or kind of correlate this thing with phase transitions. Now, if you start from let's say the front side where there is a kind of a very high cliff, okay, very tall cliff. So one side there is a land and the other side's water. So if you want to go from water to the land or vice versa, then you need to really climb or jump. Okay, so there is a discontinuity or there is a jump from the land to the water. And then if you approach a little, go little inside, and then you see that the cliff height decreases, and eventually at certain point the cliff height is almost comparable with the water level. So there, if you want to go back and forth from water to the land, then you don't need to really jump. So it's more like a continuous thing. So from here we observe two types of let's say transitions. One is discontinuous, where there is a jump from the land to the water, and the other one is a continuous transition, where you can easily go from the land to the water without much of effort or much of there is no jump literally. So this can be correlated with the phase transitions. So you have heard of this discontinuous and continuous transitions, right? So phase transitions can be divided into two parts. One is, or two types. One is the discontinuous one. The other one is the continuous. The discontinuous, it means that there is some kind of discontinuity, and you can think of some transitions like solid liquid, liquid gas, where there are some certain thermodynamic variables, they show discontinuity, they show jump. On the other hand, there are certain transitions which are called continuous, and there this jump vanishes. So an example is liquid-liquid. If you go beyond the critical temperature, then there is a continuity between the two phases. So this is overall, kind of a picture of phase transitions. Then let's go back to the textbook and try to understand, or based on certain definitions of thermodynamic variables. So the idea of defining different types of transitions, or the order of transitions, was given by Paul Enfrest, probably in 1932 or 33. And at the same time, so you see my mouse cursor, right? So the right hand side top, there are some pictures that were drawn by Enfrest back in 1930s, and he categorized the two types of transitions. He called them first order and the second order. And so the typical definition of a first order transition is they are discontinuous in the first derivative of G, which is the free energy. So the first derivative with respect to temperature, or first derivative with respect to pressure. So dG by dt is essentially entropy, minus negative of entropy. And again, the other one is volume. So that means first order transition do have discontinuity on these two properties. Now if you go back to this picture, now you can correlate this jump or discontinuity to the thermodynamic quantities, such as the entropy and the volume. You'll get you'll know more details about it as we go on. The second order transitions, instead, the first derivatives are continuous, but here the second derivative of G with respect to temperature and pressure are discontinuous. Okay, so these are the two phrases I collected from one paper, where so it was originally from the Enfrest 1933 paper. It was written in German, and if you translate the German phrase into English, then it reads first order phase transitions. And I'm sure, like me, you'll have some difficulty pronouncing the German phrase. Anyway, so this is the case. Okay, when you plot the first derivative of G with respect to temperature, then it shows kind of a jump. So you start from phase 1, and then suddenly it goes up. So here again, you can think of it as a molar entropy. So there is a little increase, and then quick jump, and then it goes to another phase. Similarly, if you think of volume, or you can think of density, then there is a jump. Instead, G, it shows kind of there is from one phase has one free energy, other phase has another free energy, and then they meet at some point. Okay, that is the coexistence point. Now, almost at the similar time, probably 1 year back, 1932, there is another guy. His name is Kisong. He was doing some experiment on liquid helium, and he was trying to understand how the phase transition. So the liquid helium exists in two forms. Let's say liquid 1 and liquid 2, and he was trying to understand if there is at all any transition from one liquid to the other, or what kind of transition is that? So he was expecting that probably it follows first or second order transitions, because by that time it was almost known. But then when he plotted the heat capacity as a function of temperature, then he saw very weird looking graph. Okay, so these are the experimental dots he connected, and it looks like the symbol lambda. And then he went back and checked, probably this is not this cannot be categorized in first order or second order, so he called it lambda transition. And then after that, many people have explored the possibility of lambda transitions, and they tried to understand what kind of transition it is, and they kind of they have given another name. Okay, it's a different type of transition. It's called lambda transition. Okay, so then we move to the Clapeyron equation. So the mathematical way to understand phase transition was given by Clapeyron, and it was based on some ideas that we just discussed, that if two phases, let's say we have alpha and beta phases, they are in equilibrium. Okay, so we have the free energy from one phase should be equal to the free energy of the other phase. So Ga, again, these are molar free energy. So G alpha from one alpha phase and G beta from the beta phase are equal when they are in equilibrium. Now, sorry, there is a mistake. If the temperature and pressure are varied, I mean, if they are changed, to still maintain the equilibrium, then we can write the change in free energy in the alpha phase and change in free energy in the beta phase should be equal. And again, from thermodynamics, we know the second law, we know that dg equal to v dp minus s dp, where v is the volume and s is the entropy. So we can write for each phase, we can write these two equations, and as we know that this should be equal, so we can write the right side of these two equations, and from there we can kind of calculate the what is dp by dt. So dp by dt is equal to the entropy change, again molar entropy change, divided by molar volume change of the two phases. Now the entropy change again can be written as the enthalpy change divided by temperature, and if you replace that one, then there comes another equation, dp by dt equal to delta H by T, and then the volume change between the two phases. So this is called the Clapeyron equation. So it kind of connects the pressure temperature with the enthalpy and the volume, and of course temperature. And then the Clausius, he kind of took a special case where he wanted to study the liquid vapor transition, and he kind of wrote down the equations in a different form. So here the enthalpy is latent heat of vaporization, and since for liquid vapor transition volume of the gas is much higher than the liquid, you can approximate the denominator as dp by dt is equal to the LV divided by T and Vg, and then if you do a little bit of mathematics to and then integrate it, and you get a relationship like this. So this is overall, like, this is the concept of Clausius-Clapeyron to kind of characterize or to calculate the dependency of pressure temperature on the phases. Now an interesting part of phase, now we talk about phase diagram. Okay, so starting from the first order, second order, and the lambda transitions, we know what are the types of transitions. Then let's say for a particular system, let's say water, if we want to calculate the phase diagram, or if you want to draw the phase diagram, how does it look like? So this is a typical, it's again generalized phase diagram, it's not for water. And so on the y-axis we have pressure, and the x-axis we have temperature. And there are many interesting things if you look closely. So there are three phases here. One is solid, another is liquid. Again, the solid is at high pressure and low temperature. So when you draw the pressure temperature diagram or the phase diagram, be careful about this excess, okay? And many a times there are confusion about the axis, about the locations of each phases. So always think about this, that at high pressure and low temperature there exists a solid, and then when you lower the pressure, then it essentially goes to liquid, and if you really make it very uncompressed, then you go to the gas. And then at high temperature, of course, there should be the gaseous or vapor state. So if you just think about these ideas, then you can correctly draw the phase diagram. And in many cases, like in interviews, we often ask students about this phase diagram, and we try to confuse them intentionally, just to kind of understand what kind of knowledge they have. So be careful about this. Okay, coming back to the description, we have the solid, liquid, and vapor phase. And there are, so these lines, they indicate the coexistence line. They are the coexistence line. What do you mean by coexistence line? It means that at this particular temperature and pressure, the solid and the vapor, they do coexist. And this line is called sublimation line. So it goes from solid to the vapor. And then there is another line which is between solid and liquid. So this is called melting curve or freezing curve. And similarly, you have another one which is called liquid vapor, okay, curve. And there are two interesting points. One point at which all three curves intersect, and it is called triple point. So why is it called triple point? Because all three phases, they meet each other. So this is a single point at a given temperature and a pressure. You just get 1 point for that particular substance, which is the triple point, where all three phases should coexist. Then there is another point which is at the end of the liquid vapor curve, which is called critical point. So this critical point is very interesting one, because up to this point you can really separate liquid vapor. So you take a test tube and then you have the liquid. What you do is you heat it up. Okay, heat it up until you see there is a little, there's so initially you see the liquid and vapor, the, what do you call, the plane, okay, interface. Then when you follow this curve and reach to this point, then you essentially, at some point, you see the interface vanishes. And that is the point where, when you know that these two phases, you cannot really separate, you cannot really tell whether this is liquid or gas. So that means it reached the critical point or beyond that temperature and pressure. Okay, and there are many interesting and mysterious things happen beyond the critical point. Okay, those of you who will be doing some experiment on physical chemistry on liquids and phase transitions, they'll probably experience this interesting thing at some point of time in your life, in your career. But then this is an interesting part. Okay, so we'll discuss a little bit more about critical point later on. Now Gibbs wanted to kind of quantify what are the variables that we can kind of keep a track on to understand this phase diagram, and he proposed a rule which is called Gibbs phase rule. So here F equal to C minus P plus 2. So F is the number of independent degrees of freedom. C is the component, so number of again independent chemical constituents. P is the number of phases, and plus 2, so 2 indicates temperature and pressure. Now these variables should be independent and intensive. Okay, so be careful with this one. And the C components, this is also something that you should really understand properly. Otherwise, you'll be misguided with things. let's say if we take a salt solution, sodium chloride in water. So if we take this example, can you tell me how many components the salt water will have? Anyone?
3 components.
Okay. Anyone else? So when you let's say dissolve sodium chloride in water, so we have sodium plus, chloride minus, and water. So it's obvious that we have 3 components or constituents. But there is a little twist here. Can you guess the twist? Anyone? If I tell you that there are 2 independent chemical components or constituents, do you agree with me, or do you have any other explanation whether I'm wrong or right?
Sir, because the number of chloride ions will be equal to number of sodium ions, so there is a restriction. So
Okay.
that is why the number of components will be reduced to 2.
Exactly. So number of chemical constituents we can say is 3, because sodium plus, chloride minus, and water. But then there is this electron neutrality restriction that kind of decreases the number of independent components to 2. So 3 minus 1 because of this restriction. So again, so this is just a, let's say, physical-chemical process where sodium chloride dissolves. So if you have one typical chemical reaction, let's say ammonium chloride, solid ammonium chloride, it goes to gas, ammonia and HCl. There you have to really take care of these restraints. Okay. Here the case is electron neutrality. In other cases, it could be the equal, let's say, amount of the gases they get released or something else. So then you get the independent chemical components. And then now going back to the phase diagram, let's say if you are in the solid phase, you take water, pure water. Okay, so we have one component, and inside the solid phase we have P equal to 1. Then what is F? F equal to 2. Right? So what does it mean? What does F equal to 2 signify? Anyone?
That we can vary either the both pressure and temperature in this regime.
Yes, perfect. So we can describe this phase using 2 independent variables, and those are pressure and temperature. And then if you, let's say, sit on any one of these lines, coexistence lines, so then you have again component 1. Now the phases are 2. So 1 minus 2 plus 2. So that's essentially F equal to 1. Now what does this signify? We can have one variable. Yes, we can have one variable that kind of describes this coexistence line. Now if you keep on doing this exercise for triple point and critical point, you will understand this number varies and you can explain it easily. Okay. Another important, let's say, thermodynamic variable or quantity we know is chemical potential. Chemical potential is very much important, and those of you who will be doing physical chemistry experiments, you will encounter many potential terms like chemical potential, electrochemical potential, in electrochemistry. So this quantity is defined as the free energy per mole. If you write the equation, yeah.
So what will be the degrees of freedom in the salt solution?
Sorry, what would be the
Degrees of freedom F in salt solution?
Okay, so the salt solution, if it is let's say one phase, then the number of components here is 2.
The 3 that will be right.
Yes. No. So the number of components would be 2 because of this electron neutrality. You lose 1, right?
Okay.
So sodium chloride, you have 3 species: sodium, chloride, and water. But there is a constraint that the sodium plus and chloride minus are same, and there is an electron neutrality restriction. So 3 minus 1 equals to 2. So C is
Okay.
2 here. And if you are in one phase, then P equal to 1, then you can calculate is 3.
Okay, sir.
F equal to 3.
Okay.
Okay? Yes.
Okay.
Now the life will be more complicated when you go from one phase to the other phase. Okay, in multi-component system. I'll just mention a little bit briefly at the end of this talk, at the end of this class. But this that is another kind of it needs another type of discussion for multi-component system. What would be the phase diagram? Okay.
Okay, sir.
Good. So the chemical potential is defined as the free energy per mole, or you can write mu equal to dg by dn at constant temperature and pressure for single component system for, let's say, pure water. But then for mixture, you can write another way, because now you focus on one particular species, and then you write for a mixture for ith species or ith component, you can write mu I as dg by dni and at constant temperature and pressure with other components at fixed composition. So this is for multi-component systems. Now, as I discussed, the free energy should be equal at the coexistence when there is an equilibrium between the two phases. Similarly, the chemical potential between the two phases should be equal when there is a phase equilibrium. Now, if you calculate or if you want to study the dependency of mu with temperature, then you can calculate d mu by dt or dou mu by dou t is equal to minus S entropy. So this is again molar entropy. Now here on right top, I plotted chemical potential as a function of temperature. And there are three lines. One is for solid, another is for liquid, and another is for gas. From here, you can anticipate that for solid, with increasing temperature, the decay or the decrease of, let's say, mu is quite less. Because in solid, the entropy changes are minimal. But when you go from solid to liquid and gas, then you see a drastic change in the chemical potential as a function of temperature. So this is something just to remember. So if somebody asks you a question in the interview, that how do you differentiate between solid, liquid, and gas? Okay, apart from those symmetries and volume, density, blah 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 thing, you can take one step ahead, and you can tell something about this. Okay, because this will give you like an upper hand. If you tell something about the chemical potential, how it looks, then you will be really, people will be really impressed. So this is something to remember. Okay, so another interesting part that I thought I should keep it in the context is the PV diagram. Do you remember the PV isotherm that I showed you in the first class? For ideal gas, if you keep one ideal gas, and you can draw the PV isotherm. Okay. Now here I have kind of collected one picture. This looks very weird, doesn't it? PV diagram. Anyone? Any initial assessment of this figure? Okay, so this doesn't look like a typical PV isotherm. Okay, it looks like a chair. And probably by now, if you had a close look at all the description of which are there on the figure, you have already figured it out that there is a little bit of twist here. It's not a pure gas, so there is a liquid to, so there is an kind of an coexistence, gas and liquid mixture. So as it is as they are marked, so you start from all liquid and you have the liquid gas coexistence in the middle, which is almost a flat line, and then there is a gas, and then the last part is familiar. We are familiar with the last part. It's a typical PV isotherm. Okay, so the twist is here we have liquid gas coexistence and the gas. So this is again at a given temperature. Here it is TA. Okay, so just TA is just a number. It can be T1, 2, 3, something like that. Now, if you focus on the right side diagram, then you see there are many isotherms. Okay, so these are, let's say, T1, T2, T3, T4, like that. So what you do is you are increasing the temperature from T1 to T2, and then this coexistence line, so this area is called coexistence area. This decreases, the width of this line decreases, and it terminates at a point. So what does it mean? So what does this point signify? So this point signify that beyond this temperature, you cannot really distinguish or differentiate between the liquid and gas. So that means from a coexistence kind of scenario, we are going to a non-coexistence, or it's like I should not say non-coexistence, but where the liquid and gas, you cannot distinguish them. So this is again the critical point, and beyond which there is a criticality. So this particular diagram is very famous because it's called the Maxwell diagram, Maxwell construction. Okay, and I think I have done something. Okay, the animation is very slow. So again, this diagram is called Maxwell construction. And this is also an important thing to understand liquid vapor, or let's say this kind of transitions and critical temperature. So the pressure that corresponds to this critical point is again the critical pressure. So you can, from here, you can have all sorts of critical quantities like PC, VC, TC, and then you know the law of corresponding states. You can derive all these reduced dimension variables. Okay, so I'm not going into those details, but you can read those in any textbook. Now, what I do is here I kind of listed down or collected few diagrams. Many of you will be familiar with these diagrams. So the first one is for the pure, let's say, water. So this looks like pure water because okay, I have a question for everyone. If I show this diagram, phase diagram to you, and I told you that this is a phase diagram of water. So what makes me think, or what gives me confidence that I can claim that this could be a phase diagram of water? Anyone?
Sir, the melting curve has
There's a
a
slope.
slope.
Okay, that's right. So usually it should be the other way around, right? For water, it has a negative slope. And now my question is why?
Sir, because volume of
So
ice is more
because
than volume of water.
volume of ice is greater.
Volume of ice is better. Do you know any other system or any other, let's say, any other system where you can have similar kind of tendency, like negative slope for solid liquid coexistence line?
Sir, gallium and bismuth.
Yes, gallium and bismuth. Bismuth, yes, probably yes. Gallium and bismuth, they show similar tendency. So there also the volume expands when you go from the liquid to the solid. Okay, and then I have another question. Okay, so now I'm remembering all the questions. So let me go back to this the other slide. This I actually forgot to mention. Okay, here I saw the. So this is not. This doesn't look like water phase diagram, right? It could be something CO2 or like that. Now tell me, I saw 2 points. One is triple point, another is critical point. I could have put another one on the solid liquid coexistence line, right? Or am I allowed or not? This is my question.
Sir, that is not allowed because there will be always a distinction between the solid and the liquid phase.
Okay, and what kind of distinction?
Means there will be a boundary separating the two at every temperature and pressure.
Okay, so yes, the answer is correct. And let me add something to it. There is something called symmetry. Okay, when you go from liquid to solid, what kind of symmetry solid has? A typical solid has. Can anyone tell? In crystal?
Long range ordering.
Yes, long range ordering, translational symmetry. It can have many symmetries, but an important thing is long range ordering, of course, and translational symmetry. For simple solids, okay, and for very complicated solids, you have to really figure out what kind of symmetry they might have. And so that's the idea, that we cannot put a point between at the end of this curve because of this symmetry. Let's say we cannot break this symmetry. Instead, for the liquid and gas, this symmetry does not exist. That's why we have a critical point. And this is another yet important question or discussion people usually tend to ask the physical chemist candidates. Now, let me ask you another thing, let me ask you another thing. Do you think if we have a liquid-liquid transition, so I mentioned helium, liquid helium, okay, so there are two liquids. Do you think a critical point might exist for this kind of transition? So for liquid-liquid transition, so here you see liquid vapor, okay. So instead of liquid vapor, you imagine we have liquid, another liquid. So do you think a critical point is possible? The answer is yes, because here also we don't need to deal with the symmetries, okay. So it can terminate to a critical point, which is called liquid-liquid critical point. And if you search in the literature, not very recently, like a few years back, people have already confirmed another critical point that exists in water. So it's called liquid-liquid critical point in water. Okay, you can check on Google. Yes.
Sir, like for solid like beta sulfur, alpha sulfur, we cannot have a critical point. Is that right?
Yes, I don't think so, because you see the solid, it is very difficult to change the symmetry going from one solid to the another solid. I mean, there is a huge change in the structure, but so these two symmetries are really separable, and you cannot really, define a particular point where they can you cannot distinguish between the two structures. So the idea about this critical point is you cannot distinguish at beyond that point, you cannot distinguish between the two phases. So that kind of scenario you may not get for solid-solid transition. So that's why the existence of a critical point for solid-solid transition is almost negligible. Okay.
Yes, sir. And sir, one more thing. In the water phase diagram, like in bachelor's degree, I somewhere read that there are 7 phases of ice.
Exactly, and I didn't put. I think I didn't. I forgot to put the phase diagram here, but yes, I had another picture where you zoom in the solid phase, and it's not 7. There are now 16, if I'm not wrong. There is a latest paper by one of my friend. He did something on molecular simulations, theoretical prediction. I think he found 11 or 16 ice phases. Okay, so there are all polymorphs. Okay.
Yes, sir.
I can send you the reference. Okay, so you can understand how mysterious water is. So one of the most mysterious chemical that we know is the water. Okay, and that's why even now people study water, only water. Okay.
Yes,
Great. So let me quickly go to the last 2 2 slides. I think we have 9 minutes. So again, I discussed about the pure component phase diagram. Again, this is water. Then we can have, let's say, mixture, multi-component. So you can have 2 types of components in a system, and then you can study liquid vapor transitions. In that case, so you'll have so you can plot as a function of composition of the particular any of one of those components, and you can draw this kind of phase diagram, and again you can check the details. Similarly, if you want to plot the temperature as a function of mole fraction of particular component, then you will get this kind of curves. Okay, and there are coexistence based on the composition, there are coexistence based on the temperature. And then for the liquid, so if you have phenol water system, so partially miscible liquid, you can draw this kind of curve. And here it is temperature versus mole fraction of nitrobenzene. I think I forgot the other component, other species. But you draw this kind of curve, and there is one point at the tip of this hill, which is called the, I think, upper critical point, beyond which you cannot really distinguish between the composition of these 2 chemicals. And then we have the eutectic mixtures for liquid and solid. So you just go through all this, have a look at all these phase diagrams. It's not very important for this course, but good to know this basics about this kind of systems. Great. So let me, again, I have this animation problem. It's very slow. Okay. Let me tell you something about what are the usefulness of what we studied so far in this class. Now again, as I told you, I'm a theoretical chemist or computational chemist. So my inclination would be towards the molecular modeling, simulations, and how do we utilize these ideas that we study in the textbook and use them to understand real life problems. Again, many of you who do experiments, you guys can understand or take the ideas from the textbook and go to the lab. You do calorimetric analysis, thermometric. I mean, there are many ITC, and then there you can calculate the enthalpy. You can estimate the free energy. You can even yeah. So this kind of all things that we study here, you can calculate doing experiments. So I take the other route. So we study we carry out molecular dynamic simulations. Again, it is similar to doing experiments. So you have to prepare your reagent, you have to prepare your input. So this is our like solvent standardization. Then when you do synthesis, in our case, we do run the molecular simulation in the supercomputer. So it runs for, let's say, 1 week, 1 month. Then as you do an experiment, you go to the analysis, you do same, TAME, whatever, many XRD. In our case, we write codes to analyze. So we kind of worked parallelly. And so here I want to demonstrate that using those ideas, once you know all these things, you can kind of compile them or use them to understand real system. I have already shown you this movie in the first class. Again, this is the conversion from a fluidic liquid CO2 to dry ice. Again, this is solid. So now you can really, you can kind of understand it more, because this is one first order transition. And now many of the experimentalists would be familiar with this kind of diagram. This is again structure factor, or you can think it as a XRD pattern, where you have particular peaks at certain K values which correspond to particular facets. This is again calculated by us. We write code to calculate the structure factor. Again, we know the positions of the atoms, and we analyze it using this Debye-Waller equations or any other the typical structure factor equation, and we get this kind of profile. So this helps us to understand whether that particular system is in the fluidic phase or in the crystal phase, because in the crystal phase there are long range orders, we get these peaks. Now we run the simulation to go from the liquid CO2 to the solid CO2. So on left bottom, I plotted some kind of order parameter. Again, order parameter is something that gives us an idea whether the system is in the disorder phase or it's in the order phase. And the x-axis we have time. So the S is kind of an order parameter. It can be anything like coordination number, the alignment of the atoms or the molecules to each other. So it's a collective, let's say, variable which embeds all the information. Let's say ordering, the distance between the atoms. So it kind of all the parameters. Like if you think of a classroom, you can calculate the distance between the two students and their orientation. If they satisfy all these parameters, then you say that all students are sitting in order, in an order. So similarly, we use this concept and kind of define a variable to dictate whether they are in the disorder state or in the ordered state. Then we run a simulation. So running a simulation means you let the system stay there for some time. So what you do is like you keep liquid CO2 and you go for your coffee and you come back. Then after let's say 10 minutes or half an hour, you see that there is a solid carbon dioxide. Similarly, here we run the simulation up to some time. Again, this is in nanosecond time scale, which is much like smaller time scale. But then we see the transitions going from the fluid phase or from the crystal, which is shown in red, to the liquid. So by doing this, we can now calculate the free energy. So we started from the system, we understood or we kind of carried out what is happening, and now we analyze and we calculate the free energy. So as I told you, this is a first order phase transition. So the first order phase transition should have a barrier. So it goes from one phase to the other phase. Okay, and if you think the free energy, this is the point where the free energy meets. I mean the delta G here, at the coexistence, delta G is equal to 0. So that means this crystal and liquid, they coexist at a given temperature. So this is the coexistence scenario. Now I talked about the liquid-liquid phase transitions. So this is again another phase diagram, but notice the pressure and temperature axes are reversed. So again, this is another example of phosphorus, liquid phosphorus, like we talked about liquid helium. Here is liquid phosphorus. So there is a phase called low density liquid and there is a phase called high density liquid. And there are some changes, structural changes. And this is again first order phase transition. But when you increase the temperature, then you see the star, asterisk mark here. So beyond this, there is a second order transition. So if I kind of map this free energy on the let's say one temperature and density plane, then if you start from this let's say lower temperature, there is a barrier. So this is first order transition. So you have to jump from one phase to the other phase. But as you increase the temperature, so from blue to red, you see the barrier vanishes. That means you are going from discontinuous to a continuous transition. So I hope this kind of gave you an idea about starting from the textbook, how we can kind of study real system and understand things in a better way. And again, you can correlate this typical phase diagram with our the first picture that I showed. Initially, you had a jump, and then slowly it vanishes when you go from first order to the second order transition. So in summary, these two classes usually I could have skipped everything and directly start from molecular modeling, but I thought it's better to start slowly and revise things to bring everyone on the same page. And from the next class onward, I will have more advanced topics on statistical thermodynamics, and then everything will be directed towards molecular modeling. Okay, so don't worry about these basic things, just revise all the concepts, then we'll start real things probably next class onward. Okay, so so far we talked about these macroscopic things like thermodynamics, but we hardly talked about molecules, although I have shown you some pictures or movies on molecules, but we mostly focused on the thermodynamic variables. But the next class onward, we'll really see what is happening inside. We'll focus on the atoms and molecules, and using the statistical thermodynamics laws or the equations, we'll try to understand starting from atoms to the thermodynamic variables. Once we do this, then we'll slowly approach to how to set up a system. Let's say I always show the CO2 system, but can we set up this system and what are the things that we need to simulate or model this process or system. That will come to those parts in the later stages. But we'll have another few lectures on theory again. Then we'll start some practical sessions. Okay, I think now we are 2 minutes ahead of the time. Sorry, we passed 2 minutes. And what I do is, if you have any quick question, probably one or two. Or if you have
Sir,
okay, so I assume that you have no questions, but if you have any
sir,
yes, please tell me, Sujan.
sir, can you just go back to the last slide where you have said that the molecular simulations? So actually, what are we doing in that molecular simulation? So the are we only that changing the phases in the simulation or
Yes.
other things?
So the idea or the purpose of the simulation was to understand how we can go from the liquid CO2 to, so we want to study the disorder to order transition. So there are let's say three targets. One is what is the mechanism, atomistic mechanism, because in experiment you don't see what is happening inside, right? Unless and until you do this in situ experiment. So first one was to understand the mechanism, atomistic details. Second one was to calculate this free energy profile. Let's say we chose one temperature and one pressure, and we plotted this free energy. You see here that delta G of these two phases is almost equal. So delta G is equal to 0. So that means this temperature and pressure that I have chosen in my simulation is on the or is at the coexistence point or coexistence line. So I chose one point on the coexistence curve and then started this transition, and it is confirmed by the similar free energy of these two phases where delta G equal to 0. So this is like a coexistence point. So the idea was to
Okay.
start with.
Is
Yes. Tell me.
is the simulations and optimization of a molecule is same or different?
No. The optimization is you see the optimization you do at 0 Kelvin temperature. Okay, there is no temperature. The simulation you have everything literally, because you need to think about the temperature, you need to think about the pressure, and then of course the volume, the molecular interactions, everything you have to think about. In the optimization problem, you only talk about the force that each of the atom uh, uh, like experiences, and there you don't talk about entropy, you don't talk about temperature. Okay, so that just if you are like really tightly bound, you release it. This is optimization. And then what you do, you walk on the streets, you interact with friends, and then whatever you do on the campus, this is simulation. Did you get the point?
Okay.
If you are
Okay. Yeah.
tightly bound, like a bad structure, and then you release it. So this is optimization or minimization. So there is no Newton's equations of
Okay.
motion. It's something like
Simulation is the oh, so simulation is the
exactly,
total culture of the molecule, right?
exactly mimicking the process. Let's say you are on the campus, you are meeting people. So the campus you can think of as a system. All the students are particles. So they do interact with each other. We have our own motions like hand one, we rotate, we translate. We don't vibrate, but we just do hand gestures and all. So these things you can correlate with the molecules. So inside a molecule, they do all sorts of things like vibrational, rotation, translation. They do interact with each other. Okay, so you really study
Yes.
the process, like you roam around the campus.
Yes.
And optimization is just releasing the stress.
Oh, okay. Okay. So
Okay, so this is just
okay.
an analogy. Okay,
Hello, sir.
yeah,
Sir, you showed two minima within the transition from the solid to liquid.
yes.
Is it the two minima will be in the same level, energy level?
No, this depends on temperature and pressure. So if you are really far from the coexistence line, do you see my slide again?
Yes, sir.
Okay, so if you are really far from the coexistence line, then maybe one phase will be much more stable than the other. So you see the delta G will go up or down depending on the temperature. So if you are moving toward the solid phase, then the crystal will get stabilized. So delta G will be, if you take delta G equal to G crystal minus G liquid, then it will be positive. So depending on this, depending on the temperature and pressure and how far you are from the coexistence line, this free energy profile will change. The minima will change.
Okay.
Got it?
So because during the MD simulation, we'll get a numerous kind of global minima and local minima.
Okay, yeah, those.
How will it distinguish that those will come under liquid and solids?
Okay, so now let's say if I tell you water at room temperature and pressure, it should be liquid, right?
Hmm.
So now if I assign the temperature, like let's say 25 degrees Celsius and pressure normal 1 atmosphere, then for this condition there will be one minimum, and water will stay there. Now if you increase the temperature or if you change the condition, then you can have another potential energy or free energy surface. It will stay there. But if you switch to, let's say, very lower temperature, then the water will get converted to ice. And if you keep the ice inside the fridge at that temperature pressure, there it will stay there. So there will be another minimum.
So we have to set the temperature at the equilibration parameter.
Yes, temperature, pressure. Because again, you see, you think about the phase diagram.
Hmm.
So you scan the phase diagram. You go at certain points of the phase diagram, and that is a function of temperature and pressure because x and y axis.
Yes.
Okay, it's like scanning the 2D diagram.
Yes.
Is it clear?
Yes.
Perfect. Okay, then so I think we wrap it up here, and next we'll meet again and we'll start statistical thermodynamics. Okay. So enjoy the day and enjoy the weekend. And if you have any question, just write to me or in the teams. We will try to answer. Okay, so enjoy the weekend. Bye bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.